This video is on heap sort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover two basic operations of heaps, including the insert and the pick methods. After we cover each method, we will also go over its time complexity analysis. Let's get started. To simplify our discussion, we will stick to max heaps, instead of switching between max and min heaps. In case you forget, in a max heap, the value of a parent node is always bigger than its children. Before we get to the basic operations of heaps, we need to do some preparations first to set up the implementation. We will prepare a class to represent the max heap. Under this class, we will define the heap size in a variable m, and use it to further define and declare an empty array named data. This array will be used to store the data of the heap. The two basic operations will be simply two functions under this class, I mean the insert and the pick methods. The insert method aims at adding a new data point to the heap while maintaining the property of a heap. So what property? In a max heap, a parent node is always bigger than its children. When you add a new data point to the heap, you may break this property. So the insert method doesn't only add a new data, but also restores this property in case if it is broken. There are three steps involved in inserting a new data point to a heap. First, you will add the new element to the bottom level of the heap, or say the end of the array named data. For simplicity, let's just assume this step is easy to do. We won't worry about whether the data array is mutable or not, or whether it's full or not. We simply would assume that it's mutable and this array named data has plenty of space for you to insert new elements into it. Second, you need to compare the added element with its parent. If they are in the right order, your job is done. If not, you will have an extra step, which is to swap the element with its parent, and then repeat the prior steps, because the new element may still be too big and needs to be further bubbled up, which involves more swapping. Let's use an example to make sense of this. Let's focus on the heap sitting on the left side of the screen, and we will add a new element with a value of 11. As you can see, 11 is added to the end of the array named data, as it's visualized here in both of the array and the above heap. So step 1 is done. As it stands now, the parent of the newly inserted element 11 is 5. So the max heap property is broken. That means we need to move to step 3 by swapping 5 and 11. So the newly inserted element 11 goes from the leaf level to the second bottom level, or say from index 6 to 2. Now we will still focus on this newly inserted element and its new parent, which is 10 now. 11, as a child, is still bigger than its parent 10, so we need to swap them, like this. And now 11 becomes the new root, which has no parent anymore, so we would stop here. One thing worth pointing out is that this tree structure you see here is merely a visualization, and the actual data is all stored in the array below the tree. As we do the swapping in the tree, we are actually swapping the elements in the array. The corresponding algorithm of this process is shown on the screen. For simplicity, we made some assumption to make this method easy to implement. Most importantly, this method as it stands now only deals with integers. If you wanted to deal with strings or objects, the comparison mechanism may need some customization. Under this assumption, the insert method takes a number as a single parameter and adds it to the end of the array. After that, it starts the process of comparing the newly inserted element with its parent. There are two things worth noting. First, the process of iterative comparison between the newly inserted element and its immediate parent is under a while loop, just in case you need to keep bubbling up the element for more than one time. If the parent is ever bigger than this newly inserted element, it means that the heap property is kept or restored, so you will break out of the while loop. Second, you rely on the generalized relationships among the indexes of a given node, its parent, and children to perform the swaps. For example, given the newly added element index as I, then the index of its parent can be calculated as I minus 1, then divided by 2. When the new element is bigger than the parent, we perform the swapping and bubble up the new element by updating the counter I. So what's the time complexity of this method? We will discuss its best, worst, and average cases one after another. The best case is relatively trivial. When you add a new element, and the element happens to be smaller than its immediate parent. In other words, the newly added element stays where it is added. For example, if you look at the heap on the left side, when you add a new element, such as 5, like this, 5 is smaller than its parent 10, so everything is alright, and the heap property is maintained. That means we will stop here. The time complexity of the best case is big O of 1. What about the worst case? The worst case happens when you add a new element that's bigger than the root. For example, if we add 11 to the heap sitting on the left side, 11 will need to be iteratively bubbled up until it is swapped to the root level. In other words, it needs to be bubbled up for as many times as the height of the heap. What's the relationship between the number of nodes and the height of a heap? This is one of the features that we studied in the past. If a heap contains n nodes, the height can be estimated as log n. In the worst case, the insert method needs to perform swaps all the way from the leaf level until the newly inserted element becomes a new root, which means that there are log n number of swaps. That said, the time complexity of the worst case is log n. Okay? Now let's think about the average case for the insert method. The proper way to conduct the average case time complexity analysis typically involves calculating the expected value, and that's how we account for the randomness, and exactly what we will be doing here. To achieve a fair estimate of the average case time complexity, we will calculate the expected number of swaps that are required to achieve the insert task. Why? The time complexity Tn is in proportion to the expected number of swaps. So instead of involving all the nuances in calculating the time complexity function, we will simplify that to the expected number of swaps. There are different ways to calculate this expected value. We will go with the simplest approach and pick the random variable here as the event when the inserted element is being swapped at each level. So that's a constant number 1. This event may or may not happen at each level. If it happens, that's a 1. If it doesn't happen, that's a 0. Beyond that, we will see the bottom level or see the leaf level as level 0, and the second bottom level as level 1. And the level number increases as we gradually move from the leaf level to the root. The probability of the event of swapping is something worth a detailed discussion. To figure out what the probability or say the pattern of the probability is, we need to clarify some assumptions first. A key assumption that we will have here is that the newly inserted element is arbitrary and random. As a result, when it comes to comparing this newly inserted element to any element in this heap, the chance that the newly inserted element is bigger is always 50%. However, you're not just doing one-time comparison between the newly inserted element and another element in the heap. You're doing it level by level, which means that each level is an independent incident. If you can just focus on the example shown up here on the screen. The first comparison and a possible swap happens here at level 1. The chance of a swap happening here is 50%. I mean, a swap only happens when the newly inserted element is bigger. That's 50%. This is the first comparison between the newly inserted element and any other element in the heap. The second comparison happens here at level 2. If you get the opportunity to do this comparison, that means you have already performed a swap at level 1. And you have to account for that in your probability calculation. Based on the product rule, the probability of a swap happening at this level, I mean at level 2, is 50% multiplied by 50%, which will give you 25%. The first 50% is how you account for a possible swap that may or may not happen at the prior level, or say level 1. This example only has 3 levels. If you have a heap of h level where h is a big number, we can generalize this probability pattern. It's worth noting that the leaf level is our level 0. As it goes up, the second bottom level is level 1, then level 2. As you go up to the root, the level number increases. Then we will say that at an arbitrary level I, the probability of swapping is 1 divided by 2, then power 2i. Meaning that you need to multiply as many 50% as there are in all the previous levels to account for swapping happening in all those levels. With the 3 things set up, you're ready to calculate the expected number of swaps. The formula to calculate the expected value is always the same. It is the sum of all random variables multiplied by their corresponding probability. When you plug in what you derive on the random variable and its probability pattern, you will have this. The random variable is 1, so you won't see it here in the formula. As you multiply 1 to something else, that something doesn't change at all. Given an arbitrary level I, the probability is 1 divided by 2, then power 2i. I goes from 0 to h, where h is the height of the heap. If you expand this formula to list a few items, you will have something like this. This is something that's not too difficult to calculate or say estimate based on geometric series. For us, all we care is to get an estimate instead of calculating it accurately, so we can relax the geometric series to infinite geometric series. In short, when you have a sum whose individual term is put together by multiplying a constant number a to r power 2k, where r is smaller than 1, then you can estimate the sum to be a constant number. And the constant number can be calculated in this way, in which you use a to divide 1 minus r. Of course, the upper cap of the sum is infinitely large. That's how you get the name infinite geometric series. Based on the infinite geometric series, you can estimate the expected number of swaps to be smaller than or equal to a constant number, as the upper cap in our case is h, which is certainly smaller than an infinitely large number. In other words, the expected number of swaps in our case is just another constant number. The average case time complexity function is in proportion to the expected number of swaps. That means it's in proportion to a constant number, so that it runs a big O of 1. Think about it. In a heap, the leaf level contains nearly half the number of all the nodes when it is full. If we assume that the newly inserted element is random, it is more likely to end up somewhere near the bottom rather than going up all the way to the root. That's the intuitive explanation why the average case is big O of 1. That's everything about the insert method. Let's move to discuss the pick method now. The pick method is relatively trivial. The only thing it does is to access and return the element at the root. So its corresponding pseudocode is just one line. That said, its time complexity will also be trivial. Regardless of if you're thinking about the best, worst, or the average case, it's always a constant time, which can be expressed as Tn belongs to big O of 1. In this video, we covered two basic operations of heaps, including the insert method and the pick method, as well as their time complexity analyses. In the next video, we will go over the last basic operation of heaps, the delete method, and dive into the topic of heap sort.